Okay, then maybe we can start now for the lecture tonight. Okay, let me start the recording. Okay, so for this one, actually, we will mention about the general method to find out the diffraction of the structure. As I mentioned before, for the general structures like a truss, like a frame, actually it is not easy to find for the diffraction. And then the method that we have mentioned before are only suitable for beam structures. So tonight we will mention about an energy method to talk about the diffractions. So first of all, we will mention about the external work and then the strain energy. And then we will mention about the principle of work and energy, principle of virtual work, method of virtual work, and then the Castigliano theorem for truss, method of virtual works for beams and frames, virtual strain energy caused by axial load, shear, torsion, and temperature, and then finally is the Castigliano method for beams and then the frames. So first of all, we will introduce you the external work and then the strain energy. Well, the method tonight that we are going to mention is actually, as I mentioned, for more complicated structures like a truss and a frame. And then, well, here we mentioned that it is the energy method that we are going to use for the determination of the diffractions. Then tonight, for the theory, actually it is about the conservation of energy principle. That means, as you can see here from the equation, the work done by the external force acting on a structure, UE actually is transformed into the internal work or the strain energy UI. So the external work done by the force should be equal to the strain energy inside the structures. They should be equal. So we use the concept of conservation of energy principle. Sorry, here again, we need to state that actually this question mark is the integration. And then, well, for this one, actually, as you know, a material can have some stages like elastic stage or the plastic stage. And then the theory that we are going to mention tonight is about that the energy are still in, the material are still in elastic. Well, if the material is still in elastic, then actually the elastic strain energy will be stored in the structures when the force is applied to the structures. And then once the force is reduced or released, then actually the structures can return to its original state, or we call it the undeformed state. Well, when a force undergoes a displacement dx, that means the force and then apply on the structures. And then with a distance of dx in the same direction of the force, actually a work will be done on the structures. So we call that is the force times the displacement. And then we use DUE to denote the external work done by the force here. If you take a look here, if we apply the force on the structures, then actually you can see that the force and then the displacement will increase in a linear dimension or in a linear manner. Then actually we can see that for each of the force, then actually for the displacement, say for this kind of the force here, for a very small force, we call that the F here. And then it goes for distance dx. Then actually this is the work done by the force. If you want to find all the work done by the force along the path, actually you just add all these kind of small elements together. And then actually forms the total area under this force displacement curve. So right here, you can see that the external work done is actually the area under this force displacement curve. So as you can see, if I apply the natural load to the bar, and at the end of the bar, F is actually gradually increased from 0 to P. So from here, you can see that originally the force is equal to 0. And then the force is applied gradually, and then up to the values of P. But as you can see here, the force actually will increase, and then the load actually under the curve is actually equal to the area. I mean, this area is actually equal to the work done by the force F. So right here, you can see that we can find the work done by the force easily. Here, you can see that it is just equal to half, and then times P, and then times the delta, which is the area of the triangle. During the force actually apply from 0 up to F, and then the displacement is equal to delta. So just like here, the external work done is equal to half P times the delta. And then when the load applied from 0 up to P, actually the work done by the force is actually expressed by this triangle. So when the force actually applied from here to here, and then actually it is equal to P, then the load will actually done the work done actually, which is actually equal to this triangular area. So we can see that the load actually right here is actually equal to P. The beam stop here. And saying that if we further apply a load F dash here, and then finally the beam displayed at this location, then actually the total work done is actually done by F plus P. The total work done is actually the area under this big triangle. However, during the loading, when F dash transfer from this location to this location, then actually the work done by the further force is actually this triangle. Then actually this rectangular area is actually done by the force P when it goes along with the deformation. So you can see that this P will go along with a deformation of delta dash. So you can see that this area is actually equal to P times delta dash. So when the force is attached here is still P, it will undergo a displacement delta dash here, then actually represented by this rectangle. And then this work done, I mean the work done by the additional force F dash actually is represented by this triangle. And then for here, for the first triangle, actually it is the first work done by the force P. So you can see that the big triangle actually composed of 3 parts, 2 small triangle and 1 rectangle. So here it is just the work which explains our total work done. That means actually composed of 2 small triangle and then 1 rectangle. And then if we have the so-called the moment, and then transfer our structures for angle theta, then for here you can see that originally the bar is here. If we turn our structures for angle d theta, so actually, well, the moment and then times the rotation, which will create the work done. And actually it is similar to force times the displacement. And then this is also the work done, but instead of moment times rotation, it is the force times the displacement. So we will take the integration for the whole. We will integrate all the small parts. Say, for example, if we have the moment here and then we have the theta here, then if we get the integration of all of them, then again, this triangular area, half m times the theta, is the work done by the force. So if you again apply the moment from 0 and then up to a moment m, then actually the moment increase gradually and then in a linear manner, then the external work done by the moment will be also equal to half times m and then times theta. And then again, if the moment is already there, and then if you have further rotation, then actually the work done will be m times theta dash. Then the half depends on whether you apply the load with the rotation of the structures at the same time, or actually the moment is already there, but it just moves with the structures together. Then actually the rotation is not caused by that particular moment. Then we do not need to include the half right there. For here, actually, we can explain the so-called the external work done and then the internal work done in a more detailed way. Now you can see that basically we have a Hooke's law. That means stress is equal to Young's modulus times the strength. And then you know that actually if I have a bar and then I have a force applied here, and then the sigma actually is equal to N divided by A. That means the stress. And then the strength is actually delta over L. Then actually we have sigma, which is actually equal to N over A. And then we have this epsilon equal to delta L divided by L, right? So we have this stress is equal to Young's modulus times the strength. By rearranging the term, actually the delta is equal to NL over EA. Then, well, if we put P is equal to N, because right now we apply the force here, we call that equal to N. Then the delta here is NL over EA. You know that actually the internal force is actually the force half times the N times the delta. Then N is here, and then delta is equal to NL over EA. So the internal strain energy stored inside the structure is N squared L over 2 EA. So this is the internal strain energy stored in the structure. Okay. And then again, if we have a beam here, I have applied the load W on the structures. And then you can see that if I consider a small element here, which have a distance of dx, then if I have a W applied on the top of the structure, that actually can cause bending moment across my beam. Then this M actually will create a diffraction of d theta. So the strain energy developed in the beam is actually due to the moment. And you know that actually this moment will cause the d theta of the structure. So actually the moment will increase and then the deformation will increase. So for here, the strain energy, again, equal to half and then times m times the d theta. Because the moment will increase from 0 and up to m, and then the diffraction will increase from 0 and up to d theta. And then you know that d theta over dx is equal to m over ei. So you have half, and then you have m, and then you have d theta is equal to m over ei, and then times dx. So m over ei, and then times dx here. Then you have half m squared over ei, and then times dx. So you have this expression here. m squared over EI and then over 2 ERX. So this is how we can get the internal string energy. If we want to find the total string energy inside the beam, we'll just integrate along the whole beam because we will add all the small elements together. Then I will find the total string energy inside the beam. Say right now, if I have a beam, cantilever beam here, and then I have a force applied here, which is equal to P, and then I want to find what is the delta here. Then you know that the external work done is equal to half times P times the delta, because the external force will do the work done is equal to P times delta and a half, as we mentioned before. And then actually within the beam, there will be the moment. And then each moment will have a work, we'll have a work done on our beam, and actually it's the string energy stored inside the beam. And then if you still remember, we will use this equation, integrate m squared over 2 EI. For that, we just derive the equation here. This is the string energy inside the beam. Integrate m squared dx over 2 EI. So for here, sorry about that, this question mark again is just integration. So we consider that there is a section X here. So here it is the P, and then this is the values of X. And then here is actually the shear, and then here is the moment. And then if you find for the equilibrium, you take the moment here on the left-hand side. You have m, and then minus px, which is equal to 0. So m is equal to negative px. So right here, you have m equal to px, and then you substitute it to here. So you have your integration negative px here. And then you integrate for this one because you will integrate it from 0 to L, and then you have negative px squared, and then dx over 2 EI, which is equal to negative COL p squared x squared over 2 EI dx, so negative 1 over EI p squared x cubed over 3 L to 0. Right? So you have the value of 1 over 6 p squared L cubed over EI. Actually, it is the diffraction, the string energy inside your structures. And then you have this string energy will be equal to this external work done because of energy conservation. So you will put half P delta equal to 1 over 6 P squared L cubed over EI. Then you could find that the diffraction is equal to PL cubed over 3 EI. Well, so this is actually using the conservation of energy. That means the external work done is equal to the internal string energy. This one seems perfect because actually you can find for the answer, right? But for this one, actually, it has some drawbacks of this calculation. We only allow one load because right now you have your cantilever structure here. And then you apply your load here, and then you have your deflection. So for this method, it only allows you to have one load to be considered. You have more than one load, then you cannot find for the delta at this location. And then the other drawback is that it can only find the displacement under the force. Say, for example, if you want to find the displacement here, then you cannot do that. So, well, this one has some limitations, and then actually we need a more general method to find the diffraction at different locations. So we will introduce you a new method. We call that the virtual work method. So for virtual means that it is not real. So for here, first of all, you need to consider structures, which is actually for any shape. And then for this structure, a series of external P is applied on that. And then actually for this P, it will cause external displacement on the structures. And then at the same time, you will cause some internal displacement delta in the structures. Because when you apply the external load on the structures, then inside the structure, there will be some stress or some internal force. And then this internal force actually will create the internal deformation due to the real load. Okay, like in this principle, actually it can also deal with the structures which are inelastic. But right now we will assume that all the things are elastic. So you can imagine this is a diagram, and then maybe it is easier to make you to understand. If you have a structure here, then you consider on the right-hand side, you have a force P1, P2, and then the P3 applied on the structures. Then when this force applies to the structure, actually it will cause deformation, or we can call it external deformation of any point of the structure. Say, consider the point A here, it will cause a deformation of delta. And then when you apply the external load, then there will be some internal force inside your structures. And then actually you will also cause the deformation of the structures, dl. So actually you have external displacement, which is dl. This is external displacement, or we call that deformation. At the same time, we will have internal deformation. So we will have external displacement and then internal displacement. Both of them are actually caused by the real load. Okay, all of them will be caused by the real load. And then right now we will introduce you a concept of virtual work. Now, virtual means something which is not new. Okay, it is not new. It is not a new real role. Okay, it is something not real. So consider the same system here. We apply a virtual force. So for example, if you want to find the diffraction at the location A, then I will apply the so-called virtual force here. Then for convenience, I will set this force equal to 1. Now, you can imagine if there is external force applied on the structure, then actually it will cause internal force in the structure. Then this external force will cause internal force in the structure. We call that as a U. So you have the virtual external force here applied. And then you will have virtual internal force here. Now you can see that, well, force times the displacement actually is equal to the work done, right? So you can imagine there's a force here which is equal to 1. And actually at the same location, there will be a deformation we call it delta. So you can imagine actually this force 1 will cause an external work done times the delta. Because you can imagine you have a force here, actually it is equal to 1. And then it multiply with the displacement delta here. So this is the external work done. And then actually you can see that there will be some internal force here, which is actually is U. And then you have this internal displacement. So you have this U here, this is the internal force. And then the internal displacement is equal to dl. And actually inside a structure, there are many internal force and then many internal displacement. So we can add them together. So this forms the so-called the virtual work method, because actually the 1 is virtual and 8 times the displacement. We can call that this one is the virtual work. This is the external virtual work done, and then this is the internal virtual strain energy. So from here, you can see that we have this equation. So this one is the dot. This one is the summation. This one is again just a dot. Okay. So 1 itself is the external virtual force. And then this delta actually is the deformation created by the real load. And then again, this U is actually the virtual internal force. And delta L is actually the real displacement or real internal deformation created by the real load. So this one actually, this one is the unknown. You do not know this one. This one actually is the deformation that you want to find. And then from the virtual force, actually this one is known. You know how to find this one. And this dl is due to the real load. This one is also be known. So you just use these two known values to find the unknown value. Okay, so this is the so-called the virtual work done or virtual work method. And then for the same time, if we consider the rotation, again, we don't use the force. Instead, we use the rotation. So we have 1 times the theta. And then, well, for here, due to the virtual moment, actually we'll create a virtual internal force. And then again, this virtual internal force will multiply with the deformation. And then we just add them together. So actually, this one can also use to find the internal rotation. But in turn, instead of using virtual, the virtual force, which is equal to 1, we use a virtual couple moment, 1. So right here, I would use the virtual work idea to find the deformation of the truss for U first. Right here, you can see that you have 2 applied load, which is P1 and the P2 here. P1 is add vertically and P2 is add horizontally. And these 2 forces will actually create deformation of the of the truss at the point B. Then for here, you can see that actually under the force P1 and P2, then actually we can create the real force inside the member. For example, this is A, B, C, D, sorry, B is right here. A, B, C, D, E, F, something like that. Then under the real force, actually, we have the so-called the real internal force. We can call the NAC, NCD, NBC, NBD, NAB, NBF, NDF, NED, NDE, and NEF here. Okay? You can see that basically under the loading, P1 and the P2, we have these forces. This is due to the real load. Do you agree? So actually, when you have the member force, then you can find the deformation of each member using this equation, NL over EA. Because actually, when you have a structures, when it is under tension or compression, then actually you will have the deformation, which is equal to delta L. And then the original length actually is equal to L. So actually the deformation is equal to NL over EA. So with the member force determined, actually we can find the internal, the member deformation for each of the member, right? So actually for each of the member with NL over EA, this is the deformation. As you remember, our virtual work method is 1 times the delta, which is equal to summation of U times DL. DL is actually the deformation of each of the member deformation. While U is the member force, by virtual force. So this is actually the DL. And this N is actually the member force due to the virtual force. Well, this is 1 times the delta. This is summation. So for here, actually, it is simple. First of all, we will multiply the values of NL over EA for each of the member. And then we will add all of them together. And then, well, we have N times, say, for example, we have NAB is the member force under the virtual force, and then times NAB over L over EA, and then plus NBC L over EA, and then add all of them together, it is actually equal to 1 times the delta. So how we can do that? Well, actually, I will just show you an example first. For example, if we have a truss here, we want to determine the vertical displacement at the joint C. So right here, we want to take a look to the joint C here, the deformation. And then under the load, 20 kN on both sides. And then we have A is the cross-sectional area, which is equal to 300 mm square. And then E is equal to 200 gigapascal. So for here, first of all, we will put the real load 20 kN here, and then determine all the member forces. under this real low. So we have this one, this one, this one, this one, this one, these several real lows. I mean, real member forces. And then as we want to find the deformation at the location C, so right here, we can apply the one here at the location C. And due to this one, we can find the member force at other members. For this one, we indicate all the member force as small letter n. And then for this one, we indicate that all the member force is equal to the capital letter N. Then actually, after finding all the member forces, we will list them in the table. So for here, you can see that this is the member force due to the virtual force N. And then for the capital letter N, it is due to the real low. And then for L, actually, is the length for each member. And then you can see that actually for our equation, it is 1 times delta, which is equal to N times NL over EA. The summation of all of them. So for here, you can see that we just use the first value and then times N and then times L. So we just multiply these three and then we can get this one. This one is actually N and L. This is for our first member, AB. And then we actually do the same for all the other member. And then we get the values of N and L. And then finally, we add all of them. And then we find for this answer. And then for 369.6, we will divide it by EA. This one actually is the dot. This one is summation. And then again, this one is the dot. So you can see that this 369.6 is actually the sum. And then we divide by A and then the E. So after doing that, we find that it's equal to 0.00616 meter, which is then equal to 6.16 mm. Do you agree? Is it okay for you? So in other words, actually, it is very straightforward. First of all, you use the real low and then you find all the member forces one by using method of join or method of sections. And then secondly, you will put the put the force at the location where you want to find the deflection. Say, for example, if you want to find the deflection at C, then you will put the point low at the C and then find all the member force inside the truss. Afterward, you will list all the forces due to the virtual force and then the real low, and then you will just multiply them together. And then you can find for the value. After that, you just add all of them together. And then divide by EA. So actually, if you understand this idea, you can further extend it to other situations. For example, actually, when there's some temperature change, say if the temperature increase, actually it will cause the member to increase the length. Then actually you will use a temperature coefficient alpha. And then this is the change of temperature. So you can find a change in the length due to the change in the temperature by multiplying with the coefficient of temperature. Then actually the deformation before actually, if you multiply, is N times NL over EA. So it's the virtual force or virtual member force times the deformation. And right now the deformation is due to temperature change. So again, you can use the deformation here. This is due to the temperature change, deformation due to temperature change, and then times the virtual force in the member, and then you add all of them together. Then actually it is equal to the external displacement. That means actually you can find the deformation of the truss by considering the deformation of each of the member due to the temperature change. Well, by using the same idea, actually you can also find the fabrication error. So for here, you know that due to the error in the length of the member, sometimes it is a bit too long and then sometimes it is a bit too short. Then actually it will cause the structures to have deformation. Well, you know, when you fabricate your member, sometimes it is not perfect. Sometimes it is shorter than you expect. Sometimes it is longer than you expect, right? Then actually, well, the change of the displacement will also cause the overall change of the structure. Because if the member is a bit too short, then there will be a change of the length in a negative sense because it is shorter. If the member is a bit too long, then actually the length will increase. Then the delta L will be a plus in the length. Then actually this is the length due to the fabrication error. And then this is again the virtual member force. And then this is times, and then this is summation. Okay, so again, you can find for the answer, okay, for that, due to the fabrication error. So this is the second example that you can take a look. Now you can imagine this truss, and then there's no loads applied on the truss. But right now, you can see that we assume that the member AB is 5 mm too short. Then we want to determine what is the vertical deformation of the joint C here. Now, if you think of AB is too short, then what will happen to the joint C? Now, if you think that AB is too short, then actually when AB is shorter, then actually the joint C will go up, right? So actually there will be a deformation of the joint C. Then to find the deformation of the joint C, we will apply the unit load, which is actually the virtual force at the joint C. Because we want to find the vertical displacement, then the virtual force will apply in the same direction of the displacement. So we apply the vertical load, which is equal to 1 to the structure. So if you apply 1 here, then you can find the internal force using method of joint and the method of section. Then you know that actually just the bottom member will have a deformation because of so-called the fabrication error. It is 5 mm too short. So again, we have 1 times the delta and then summation of n times the dl. Then, as I just mentioned, there's only deformation of the bottom member. It is 5 mm too short, so it is negative 0.005. and then times the force. And then we can find that the value is equal to 3.33 mm. So that's why, well, we can find that it is equal to negative 3.33 mm. It's the change in the vertical deformation. So that means if the bottom member is 5 mm shorter, and then actually the vertical deformation is equal to 3.33 mm. And as the load is pointing downward, negative means that it will, the deformation will be upward, okay, in the negative direction of your assumed direction. Do you agree? Now, the Castigliano method actually is similar to the virtual force method or virtual work method. And I will introduce in the next lecture. And right now, I will use the virtual force or virtual work method for the beam and then for the frame structures as first. So for here, actually similar to the truss, actually we can apply the method to a beam or a frame structures. Again, the question mark, the first one is equal to the dot, and then the next one is equal to the integration. Now, you should still remember the equation actually for the truss is 1 times delta, which is equal to n, and then summation n, and then NL over EA. This is the virtual force in the member, and this is the deformation of the member. And then by the similar method, actually for the beam, we will have the N here. This is actually the internal force in the member, and then this is the virtual moment in the beam. And then this is actually the deformation, delta L. And then, well, this is DL. Then for moment, you know that the moment is actually m times theta. So right here, well, you can see that this one is m over EI. And then you know that d theta over dx is equal to m over EI. And then we can write down d theta is equal to m over EI and then times dx. So right here, this one is actually the d theta, okay? And actually, this d theta is considering a small part in the beam. We just consider a small element here, and then the distance is equal to dx, right? And then if you want to find the string energy within all the beam, then say this is 0, this is L, then we need to add all the elements within the bar. So actually, we will have integration from 0 and up to L. So this is external work done, and then this is the string energy. So it is m times d theta, and then we will have our integration. So the overall equation is 1 times delta. This is the external deformation of the beam, which is equal to integration m over EI, and then times the d theta, dx, sorry. So it will integrate along the whole beam. So right here, you can see that if you want to find the deformation in the beam at this location, then we will consider two things. First of all, we will have a beam, the same beam, and then apply the point load here, which is equal to 1 kN. And then from that, we will find the virtual moment M. And then for here, for the real load W, and then have a X system here, we will find also the virtual moment. This not virtual moment, it's the real moment M. And then if we find both M and then small letter m, then the deformation is equal to mm over EI dx and the integral from the start to the ends of the beam. So this is the way how we can find the deformation at any location within the beam. Instead of finding the so-called deformation, we can also find the rotation. Say, for example, we want to find what is the rotation here. What is the rotation of the beam here? Then instead of using point load, we will apply the so-called point moment here, or we can call that a unit couple moment. By applying the unit couple moment, we will also find the virtual moment. And then we still use this real moment. And then this time we will use this virtual moment here and then the real moment here, and then we can find for the rotation instead of the deformation. Okay? So if you want to find rotation, you use a couple moment. If you want to find the deformation, you use a point load. Okay? Do you agree? So actually the same equation can be used 1 times theta. Actually it is equal to the integral of moment. This virtual moment is due to the couple moment. And then again, this is m over EI and then times dx. So here I will just use an example to illustrate to you the idea. We want to find the displacement at the point B of the steel beam. So we want to find the displacement here. Then how can we find that? Again, we can use, don't forget that we want to find the displacement, then we have this equation. M, for the small letter m, actually it is due to the point load applied at this location. Then I can find the virtual moment. And then for here, for the beam, this one, I can find the real moment. And I can substitute the values here, and then I can find for the deflection at the point B. Then first of all, I will put the point load at the ends, and then I have an X here. And then for the moment, I have 1, and then which is equal to negative 1x. This is the moment equation due to the virtual force. And then for the distributed load here, it is equal to 12 kN per meter. And again, you will cut the same section here, and then you can find that the the real moment is equal to negative 6 and then times x squared. Now, I think you know how to find for the moment functions, right? Now, remember, they need to use the same coordinate. This is x here, and then this is x here. And then, well, you will put the small m here, which is the virtual moment. And then you will put the large m here. This is the real moment. And then this is time value, and then you will put the integration here. Then for here, actually, you will have 0 and then 10. And then this is 6x cubed over EI, and times the dx. Then you know that this is 6 x4 and then divided by 4 and then 10 to the power 0. So this is 15 times 10 to the power 3 and then divided by EI. So actually this is the answer. And then if you substitute the values EI, then you can find for deflection at the beam. Okay? You know what I mean? So you just put the virtual moment and then the real moment, and then you just integrate it. Then you can find for the deflection at the B. And then right here, you want I would like you to determine the slope at the point B. While we apply the force 3 kN in the beam. So if you want to find the slope at the B, so first of all, for the real load case, you will find the moment here. And then for another beam, you actually have the B here. And then if you want to find for the rotation at the B, so you apply 1 here. Then you can find for the M. This is the virtual moment. And then, well, you can find the deflection, which is equal to integral MM over EI and then dx. Okay. So basically, it is just the virtual moment and then multiply with the real moment over EI and then times dx. Then you can find for the rotation. Well, actually, you can use a different system. Now, first of all, you can assume that all your x start here, and then to find your moment function. Or in the book, actually divide the section into 2 parts. The first coordinate system is start from A. So from here to here, you can see that this one is 5 meters and this one is 5 meters. Now in the book, actually consider 2 systems from here to here. They call it the X1. That means they use the ends at the origin. And then they use the B as the origin as well. Here they use as X1, and here they use as X2. So from here, it is 0 to 5 meters. And X2 again, it is 0 to 5 meters. Now, for the 2 coordinate system, actually you have the same way to find for the moment. Say, for example, right here it is X1. And then you can see that if you put the shear here and then the moment here, if you cut the free body here, then you can see that actually there's no loading on the left-hand side of the beam. So the moment will be equal to 0. So this one is straightforward. And then if you cut a section here and then you consider the origin is at the point B, then on the left-hand side, actually, there's a 5 meters. Then if you have 1 here, then you have also 1 here. So the moment for the second section, where X2 is between 0 and then the 5 meters, then actually it is equal to 1 again. Well, if it is 3 here, then again you cut 2 sections. First of all, you will cut X1. Then you can see that this is 3. 3 times X1, it is counterclockwise sense. And then plus M, this is M1, which is equal to 0. So M1 is equal to negative 3 X1. So this is for the first equation. And then for the second equation, you can see that is the origin start from point B. So this is x2. So in terms of x2, we want to find the moment here. So you can see that the total moment arm is 5 times x2. You should take moment here. So you have 3 and then times 5 plus x2. Then you have your m2 here. And then you have plus your m2, which is equal to 0. So m2 will be equal to -3 and times 5 plus x2. So it is actually this one. Okay. And then if you take a look to the moment function, you can see that actually the bending moment is equal to 0 at the first, and then it actually will go up like that. So you can see that this one is just like a rectangle. And then if you consider this one start here, then the bending moment diagram is actually a triangle here. And then within this zone, actually it's just like a trapezoidal area. So you can see that from the shape of the diagram, it is just a rectangle. And then multiply with a trapezoidal area. And then actually your integration, of course, you can do it here. This is the small m, 0 at the first, and then it is equal to -3x1 here for the first part. Because actually it starts from 0 to 5. And then for the second coordinate system, also it starts from 0 to 5. So for the this part, the virtual moment is equal to 1. And then the real moment is equal to -3 times 5 plus x2. So after the integration, you can find the value is equal to -112.5. Negative means that it is, well, in the opposite direction of this one. So actually it will rotate in this direction. And then I just mentioned that in terms of the shape of the bending moment diagram, actually one is a rectangle, the other one is the trapezoidal area. And actually you can use a so-called integration table. Then you have the rectangle here and then multiply with a trapezoidal area. So from here, this one is, first of all, is m. M is the moment here. And then this is m1 dash plus m2 dash. This is m1 dash plus m2 dash here. That means it is the length of the size of the trapezoidal area. So you have here is equal to -15, and here is equal to -30. So -15 and then -30 here. And then times the distance of 5. This is the L. So actually this integration can be done by using the so-called the integration table. But of course, you can do it by using the traditional integration. Okay. And actually the same method can be extended to a frame structures like this. Now, here you can see that we can determine the horizontal displacement of point C. You can see that we have a point C here of the frame. And then, for example, when you apply the force, it will be something like that. Right? Then you have the so-called the horizontal deformation. Then to find the horizontal deformation, actually we will apply a 1 kN force on the structure. So again, we will consider two cases here. This is our frame. And then I have a pin here, and then I have my roller here. First of all, I will have my distributor load here. And then this is 60. And then I will find for my real moment. And then for here, actually I will have my frame here. And then I will apply the values of 1 kN here. And then I will find for my virtual moment. Okay, then we again use the so-called the same equation. We call that m over EI and times dx, which is equal to delta. Okay, then first of all, we applied our 1 kN on the structure. Then by using equilibrium, we can find the support reaction at the member. Then actually, first of all, we can cut our free body diagram, saying that we start from the end of the bar here, and then find for the moment, M1. Then if you have the bar here, and then you have the 1 here, and then you have 1.25 here, and then you have X here. And then you just assume that this is the vertical beam. So you will apply the shear here, and then you apply the moment here. Then from here, you can find for the expression for M1. You use summation of moment is equal to 0. And then you have M1 here, which is counterclockwise sense, and then negative 1 times X, and then which is equal to 0. Then M1 is equal to X. So you have this equation for your vertical moment. For the horizontal member, you can start your coordinate system from here and then point to the left-hand side. So you have your M2 here. And then again, you will summation of moment is equal to 0. Then you have 1.25, and then times X2, which is a negative value, and then positive value, and then minus M2, which is equal to 0. So M2 is equal to 1.25 X2. So you can find for the virtual moment of the vertical member and then for your horizontal member. And then at the same time, we can do that for our vertical member under the real load. So under the real load, we can find for the support reaction here, here, and here. And then you can cut for a free body diagram. And this is the shear and then the moment that at the member ends. And then you can consider the equilibrium, and then you can find for the moment equations. M1 and M2. And then again, you use the same equation. That means it's the MM over EI, and then take the integration along the whole member. So this is the virtual moment, M, and then this is the real moment, M. This is for the vertical member. And then this is again the virtual moment, M. And this is the real moment, M. This is for the horizontal member. So you can see that this is the 3 meter and this is a 2.4 meter. So here for the vertical member, you integrate along the whole member, and then for the horizontal member, it is also 2.4. And then you can add them together. Totally, you can find the horizontal displacement is equal to 1660.5. If you take a look to the bending moment diagram, you can see that first of all, for the real load, actually there's a triangle here. And then there's a parabolic shape here for the vertical member. And then for the virtual force well members, you can see that both of them are triangle. Again, if you take a look to the integration table, well, triangle to triangle, you can have this expression. Triangle to parabola, then you can have this expression. So you can see that, well, this one actually equals to this one. 5/12 and then times 3, and then times 270 and then times 3. And then for this one, actually, it is the expression for this. Then again, you can use this integration integration table to find for the values 1660.5. So by substituting the values of E and I, then you can find for the answer for the horizontal distance, which is equal to 35.3 mm. So is it okay for you? Now, I think this one is quite straightforward, but I think you need some practice for that, because you need to know how to write down the equation and then do the so-called integration. So the integration is very elementary. It's not very difficult, so don't worry about that too much. But I still think that you need some practice. Okay, then I think that's the material that I'm going to mention today. I have the Castigliano method that I will mention in the next lecture. But before the end of the class, let's discuss something. Let me close the recording first. Okay. Then I will go to the Moodle first. Wait for a moment. 嗱，我擺咗份功課喺度㗎啦，咁所以咧大家咧就要去做啦。咁咧我就俾2個禮拜時間大家嘅，咁就2號。咁你哋翻去試下，咁做完就交啦，好冇？另外一樣嘢咧就係差唔多要測驗㗎啦。咁咧我就約咗個時間啦，因為我唔想嘥咗上堂嘅時間。咁咧，如果我知道你哋大家咧有唔同嘅 schedule， 即係你知啦，好多時你哋大家上堂咧有啲星期唔同啊，即係平時夜晚咧就好難測㗎啦。咁咧就我就 propose 咧揾一個星期六。咁我而家咧就想5號11月5號嘅7點鐘就測驗。夜晚黑我諗大家都唔使上堂㗎啦。咁咧就因為都而家所有嘅測驗都要 face to face 㗎啦，全部都要翻嚟。咁咧我就想約大家咧5號嘅夜晚7點就翻嚟 DI 呢度做個測驗嘅，有冇問題？11月5號7點 ，OK。嗱咁就個房咧我 book 咗，我話俾你聽嘅。但係咧就即係大家畫一畫低個時間啦。星期六11月5號7點，唔係 online 㗎嚇，係翻嚟學校測，因為而家全部都要 face to face 㗎啦。咁7至9度啦，測2個鐘，好嘛？有冇問題 ？OK， 考到邊度咧？考到第5課，即係 deflection，我哋上一次課教嗰度。考到 deflection 即係 conjugate beam 嗰度，第5課有冇問題 ？OK， 我會 post 喺 Moodle 噶啦，咁就即係大家容易啲啦，好嘛 ？OK， 好，咁如果冇問題咧，我哋今晚到呢度啦，咁我唔會即係太夜啦，今晚好嘛 ？OK， 咁就有問題就問啦，冇問題可以走啦。